right, so we're going to start with density curve definition. There's two criteria that have to be met to... What's with everybody leaving? We barely started. Two criteria that have to be met to qualify a curve as a density curve. Sorry, I moved all my pens away from where I need them for some odd reason. So the first criteria is that the curve is always on or above the horizontal axis. And this is one that we tend to assume. Very rarely, unless there's a question that is specifically asking if a density curve is legitimate. Very rarely do you ever see the horizontal axis labeled. So you need to know that it is part of the definition, but you'll see in a minute when I show you a density curve that we don't actually ever draw the x-axis and label where the origin is. I don't know why. We just kind of take it as a given. And then the other criteria is that the area under the curve is always 1. My lights are driving me crazy. Can you guys see the change in the lights?
I love watching you react to my chats.
I'm glad you knew it was your chat too.
I only have those dreams though, like when I sleep through your class. Like when I take an afternoon nap, like during lunch, and I sleep through stats, I wake up and I have a dream that Chloe told me you hated me.
Well, don't sleep through my class and then you won't have those dreams, Taylor. But you're here, so I don't hate you. Yes.
I'd like to say you're welcome for always waking her up with my dreams.
Thank you, Chloe. I do appreciate that.
Yeah, but when Dream Chloe wakes me up, I don't want to go to class because I feel like you hate me.
I don't hate you, Taylor. Oh my goodness. All right, so just some... characteristics, I guess is the way to say it. Density curves describe the overall pattern of a distribution. And we're going to look at special density curves. Sometimes I wish I could write faster. Or write like as fast as I say the words, because I like say it and then I feel like there's this huge awkward silence because I'm then writing the words. I'm abbreviating distribution as dist. Can't spell. I need to mark the Dylans here. All right, and then the other important part, and this is going to sound, at least in my opinion, it's really convoluted, but it's not as difficult as it sounds, and it's actually going to be the focus of what we do today. But putting it in a sentence to me just sounds weird. So the area under the curve and above any interval, I can't do that. Sorry, I was trying to write and read at the same time and I just can't. So area under curve and above any interval of values on the horizontal axis. And I'm going to abbreviate horizontal axis as HA just because I'm lazy. Is the proportion, and proportions can be written as decimals or as percents. And today we're going to focus on the percents. So area under the curve and above any interval of values on the horizontal axis is the proportion or percent of observations in that interval. So we're going to find the percent of observations that fall in a certain interval. But we're going to use a density curve to help us. And not just any density curve, the most special density curve of all time, the normal curve. Tried to make it sound really cool and suspenseful, and I think I kind of failed. An interesting fact, although I'm going to be honest, I'm never going to ask a question about this on a test, so if you kind of let it go in one ear and out the other, that's okay. So when you're looking at the median and mean of a density curve, what is known as the equal areas point, so splitting it in half, would be the median, which makes sense because the median is the middle point, and it breaks the data. It's the 50th percentile. It breaks it in half. So it makes sense that the median would be what is known as the equal areas point. The mean, on the other hand, is what we call the balance point. And this one, even I struggle with this, but if we were to take a density curve and make it out of a solid material and balance it, the point that it balances on is where the mean would be. Of course, if your curve is symmetric, they happen to be at the same place. And like I said, we're going to focus on the normal curve, which in a minute when I define you'll find out is symmetric. So the mean and the median are at the same place. Like we talked about in Unit 1, if you have a skewed curve, the mean is pulled away from the median in the direction of the long tail or the direction of the skewness. And I apologize, I was trying to underline and I actually crossed out words. It's a good thing I don't teach English, right? They underline a lot. So like I said, we're going to focus on the normal curve. So a few extra characteristics about normal curves. So normal curves, I guess I'll just write it down because I don't want to say it like 4 times, and then I'll give you my other point. Sorry, I'm just thinking about when I want to say it. So I'm just going to say it now. We're going to skip down to this first bullet point in this box. So normal curves all have the same overall shape. And that shape is symmetrical unimodal, and bell-shaped. And the whole point of me saying this was, you'll see in a minute, I put templates in the notes. A normal curve looks something like this. Okay, so that's a normal curve. Density curves can take on a lot of different shapes. They can have skewness, they can be uniform. So you could have a density curve that has skewness. You could have a density curve that's uniform. Okay, oops, sorry, that one's off the camera a little. That's uniform. We're gonna focus on normal curves that are symmetrical, unimodal, and bell-shaped. And so our density curves, they only have to meet those two criteria. Normal curves have more criteria that they have to meet, and that's what we're gonna go through now. But some interesting facts. Now I feel like I should finish down here and then go back up there. Sorry, I'm second guessing myself. I'm just gonna go with the way I had it. So normal curves are an important class of density curves. So there are other density curves. Like I said, they can be skewed, they can be uniform. Lots of different types of density curves. And normal curves are just an important class of density curves. Normal curves only describe normal distributions. So density curves give you an overall pattern of a distribution. Normal curves only describe normal distributions. And yes, we do capitalize the word normal. And this next one is my favorite, and it's the reason why we capitalize the word normal. Honestly, I don't care if you capitalize, but know when you see me write normal with a capital N in the middle of a sentence, technically it is correct in statistical grammar. And the reason why is because normal curves are not normal at all, and they are quite special, and we denote that by capitalizing the word normal in the middle of a sentence. And then our last one, and this is really just to reiterate it because it's one of the criteria of a density curve, and that is that the area under the curve is equal to 1. And I also love to tell kids at this point that we are doing calculus because we are. In calculus, all you do is find the area under the curve. When you find derivatives, you're finding the area under the curve. When you find integrals, you're given the area and you find the equation. Well, we focus on a special curve in statistics, and we do calculus with it. So even if you haven't taken pre-calc or calculus, we're doing calculus. And to me, it's the only calculus that's important. So, then some nice characteristics about normal curves. We talked about how they all have the same overall shape, symmetrical, unimodal, and bell-shaped. They are completely described by mean and standard deviation. Now here's the weird part, because it's math. We no longer use X bar. We use mu. It's a Greek letter. To me, it kind of looks like an M, kind of looks like a U, depending on how I write it. But that's it. And it does start higher on the left and lower on the right. It's a weird letter. And standard deviation, we were using S sub x, and now we will be using sigma. And really the reason why is because if you're looking at a sample, so a set of data, you use X bar and mu, or X bar and S sub x. And if you're looking at a distribution, which you can assume it covers the whole population, then you would use mu and sigma. And we're going to be making sketches for a lot of the problems here on out, and you need to label your sketches. And I'll show you on an example problem in a minute, but you need to label them with a capital N, and that stands for normal. And then you put parentheses, and it's going to look like an ordered pair, and you put your mean or mu and your standard deviation or sigma. And like we talked about up here, the median and mean are the same for a symmetric density curve. Normal curves are symmetrical, so the mean and the median are both at the center of the distribution. And I'm going to abbreviate distribution there. And then the last one, standard deviation. Sorry, Nate, I just saw your comment. If they're not normal at all but special, why are they called normal? That's a good question. Because I don't know. So we could, okay, here's my thought process, but I don't know if this is correct, because we can take any distribution and we can eventually take a large enough sample size, or we can standardize it using z-scores to make the shape of the distribution look like this. And so it just became the normal shape. I don't know if that is the real reason behind it, but that's, like, when you asked it, that's where my brain went to, because we can eventually take any distribution and make it look that way. So then it's normal looking, I guess. And then the last characteristic, which to me is pretty intuitive, standard deviation, which is a measure of spread, controls the spread. So if you have a larger standard deviation, you're going to have data that's more spread out. Even if the picture, the sketch looks the same, if you have a larger standard deviation, the data is more spread out. And maybe that's why it's normal, because no matter what your mean and your standard deviation are, they all look like that. I don't know. That's a good question. I'll try and find a real answer for you, Nate. Standard deviation controls spread. So that means larger standard deviation. Data more spread out. I apologize. That grammar is not the best. And now we get to get away from definitions. Yes. And we get to do some math. I don't know if I'd really call this math. It is math. And we're going to use symmetry a lot. Am I okay if I go to the next page? Thank you. I saw nods and thumbs up. I guess we have technically one more definition. Gosh. Sometimes I wonder how I got into statistics, because I'm not a wordy person, and there's a lot of words in statistics. Kind of drives me insane. All right, so all normal distributions obey the following rule. If you watched the crash course video yesterday, it was the first video that I had for you guys. They talk about the empirical rule, and this is what we're going to focus on right now. So in a normal distribution with mean mu and standard deviation sigma, approximately 68% of the data falls within plus or minus 1 standard deviation of the mean. Approximately 95% of the data fall within plus or minus 2 standard deviations of the mean. And then approximately 99.7% of the data falls within plus or minus 3 standard deviations of the mean. Oh my gosh, can you guys see the change in the lights on the notes? It is driving me insane how much my lights are fluctuating. Casper is really messing with me today. So, I personally am a visual person, so just seeing it in words isn't the most helpful. So we're gonna draw it on our normal curve. So remember our sketches, and I'm gonna do my best. I'm not gonna be perfect, because I'm just not perfect. But I'm gonna do my best to make sure I give you templates if you need to draw it. On your homework tonight, you're gonna see we're gonna use the same distribution for like 6 different questions in a minute. On your homework, instead of giving you 6 templates, I just gave you 1. So hopefully one's enough. You can always work in pencil and erase and then draw things if it helps you. Or you could draw a normal curve by hand. They're really not that hard, and honestly, if they're not perfect, I don't care. So first thing, capital N, it's normal. Our mean is mu, and our standard deviation is sigma. Now, one of the characteristics of a normal curve is that your mean is at the center. So down here, and this is what I was talking about with that first density curve criteria, that it has to be on or above the horizontal axis. This qualifies, even though nowhere does it say it's on the x-axis or here's the origin or anything. That's what I was saying. We tend to just assume that that is happening. But they don't actually usually specify that it's on or above the horizontal axis. So down here you can see the little hash marks. The hash mark in the center we're going to label with mu because that's our mean. Each hash mark represents a standard deviation. So here's 1 standard deviation above the mean, 2 standard deviations above the mean, 3, or 1 below, 2 below, and 3 below the mean. So we're going to label those. I'm going to turn it sideways because otherwise my labels are going to run into each other. So this hash mark is the mean plus 1 standard deviation. This one is the mean minus 1 standard deviation. The mean, if I go 2 hash marks above, that's the mean plus 2 standard deviations. If I go 2 below, that's the mean minus 2 standard deviations. And then you guessed it, this one is the mean plus 3 standard deviations and the mean minus 3 standard deviations. Are you guys okay if I turn it back the right way? Thank you. All right, so between 1 standard deviation below and 1 standard deviation above the mean, our empirical rule tells us that we have 68% of the data. So in that center there, I don't want to color it in because I'm gonna put a couple more on there, but if I were to color it in, that would make up 68% of that curve. The empirical rule tells us that 2 standard deviations below and above the mean give us 95% of the data. And then our last one, 3 below and 3 above, give us 99.7%. And I apologize, my line was not straight. So we're going to use that rule plus the fact that normal curves are symmetric to answer some questions. And this, I swear, is my absolute favorite example. It's actual data. It's an actual test, but it always cracks me up. And we'll see if any of you pick up on why. Can I move it up? All right. The distribution of ITBS, the Iowa Test of Basic Skills vocabulary scores for 7th graders in Gary, Indiana, is normal with a mean of 6.84 and a standard deviation of 1.55. Anybody know why that's weird? What's weird about that? Sorry, I liked Emma's reaction. She seems to be reading it really hard. Are you going to get it, Emma?
No, I'm not wearing my glasses, so it's like hard to read. So
Gotcha.
I have to put my ear.
Gotcha. Man, I thought you were just trying really hard to find the funny part for me. It's really not funny. I just find it funny, I guess, because I'm weird. It's the Iowa Test of Basic Skills, and it was given to kids in Gary, Indiana. Like, why would they take the test from Iowa and give it to kids in Indiana? Or at least change the name to the Indiana Test of Basic Skills. I don't know. It gets me every time I use this example. And like I said, it's real data. It's an actual test that was given to actual students in Indiana. It's just weird to me. All right, but back to math. So this part right here, Remember, that completely describes the normal curve for us. So what that tells us, the capital N tells us we're working with a normal curve, which I kind of gave away by putting the templates down there. The first number is your mean. The second number is your standard deviation. Sorry, Chloe sent me a message and she called me queen, and I don't know why she called me queen.
Why wouldn't I call you queen?
I don't know, because I'm not a queen. All right, sorry. So, like I said, capital N tells us that it's a normal curve. And then the first number is your mean. So mu is 6.84, and standard deviation, or sigma, is 1.55. So in our picture up here, we use the general notation, mu and sigma. Well, now we know the value of mu and the value of sigma, so we're actually going to fill in numbers for our hash marks. And where did I put my calculator? There it is. Again, I'm going to turn sideways so that I don't run my numbers into one another. I suppose, you know what, I'm going to do it this way, because this is how I'll do it with other ones. Sorry, changed my mind. So mu, the mean, is at the center. So that is 6.84. And then I'm just going to drop the label for those hash marks down a little. So this hash mark is my mean plus a standard deviation. My standard deviation is 1.55. So I'm going to do 6.84 plus 1.55, which gives me 8.39. The next hash mark is the mean plus 2 standard deviation. So I'm going to take my 8.39 and add another standard deviation, which gives me 9.94. And then this final one, which is 3 standard deviations. So I add 1.55 to my answer, and I get 11.49. And then I'm also going to subtract standard deviations. So 6.84 minus 1.55, which is 5.29. And then I'm going to take away another one. That means this one is 3.74. And take away one more. And that gives us 2.19. So when you're given the mean and the standard deviation, then you can find actual values for all those hash marks. So then we can answer questions like, what percent of the ITP, as that like came out in a mumbo jumbo, sorry. What percent of the ITBS vocabulary scores are less than 3.74? So here's 3.74, and that is 2 standard deviations below the mean. 1, 2. So I'm going to use my rule that tells me that 2 standard deviations below the mean to 2 standard deviations above the mean is 95% of data. Now I'm looking for this, let's see, I'm going to use a different color. I'm looking for the percent in this little tail here. That's what I want to find, that little orange tail. So I know from that empirical rule that 95% of the data is between 3.74 and 9.94. Under the curve, I'm going to have 100% of my data. So I can subtract 95, which tells me that for this tail and this tail, I have 5% of my data left. The characteristic that normal curves are symmetric tells me that I have equal amounts in each of those tails. So if I have 5% for these two tails, I'm going to cut it in half, and that means that 2.5% of my data lives there, and 2.5% of my data lives there. So I'm just going to write a little paraphrase. Because of symmetry, we know the remaining 5% is evenly split. So, what percent of the scores are less than 3.74? 2.5%. Questions? No questions? All right. So here we're going to look at what percent are greater than 5.29. So I'm just going to quickly label this 6.84. This one is 8.39, 9.94, 11.49. That is 5.29, 3.74, and 2.19. All right, so this time the question is what percent are greater than 5.29? So here's 5.29. And we want to know what percent of scores are greater than that. So we want to find this whole area under the curve. And so again, we're going to use our empirical rule and the fact that we have symmetry to help us figure out the percent. Bye, Chloe. So 5.29 is 1 standard deviation below the mean. So I'm going to work with 1 standard deviation above and below, which our empirical rule tells us is 68%. So same idea as with this one. We know 100% of the data is below the curve. We've accounted for 68%, which leaves 32%. Because of the symmetry of our normal curves, that tells us that 32% is going to be evenly split for this tail and this tail, and half of 32 is 16. So we have 16% there and 16% there. So, to find the percent that I shaded, 68% plus 16% would give us 84%. So 84% of the scores are above 5.29. questions? No? Okay. We're gonna still work with the same distribution. So I'm gonna label my normal curve again really quick. This is 6.84, 8.39, 9.94, 11.49. When you're labeling your normal curves, unless it specifically says to label all of the distribution, if you just label the ones that you're interested in, I'm totally okay with that, so that you don't have to go through and label each one. I'm going to label each one so that hopefully I'm as clear as possible, but you guys don't have to if you don't want to. So this one, I'm going through my lesson last period. I should have started with this question, but that's okay. We're going to do it now. So we're looking at what percent are between 5.29 and 8.39. So here's 5.29. Here's 8.39. So we're looking at this area. And that is 1 standard deviation below and 1 standard deviation above. So that is 68% just because of the empirical rule. No extra symmetry or anything. That's why when I got to that one, I laughed at myself. I should have started with that one, but you'll see why I have that one there in a minute. I did have a thought process. All right, so then the next one asks us to find the percent between 8.39 and 9.94. So 6.84, this is 8.39, and this is 9.94. So that would be this area that we're interested in. So we're going to use some of our results from previous problems, and you will notice in your homework that a lot of times they kind of like build on each other, which is pretty typical of any math class. So our lower bound here of 8.39 is 1 standard deviation above the mean. So using our empirical rule, I know that from 5.29 to 8.39 is 68%. From B, so sorry, I'm going to move this down. From B, so this problem here, we found that 68% in the middle leaves 16% on each tail. So from 8.39 through the end of the curve is 16%. From A, we learned that 9.94 through the end of the curve is 2.5% of our data. So to find what percent is in the red area, I would take 16, that whole tail, minus the 2.5% of the tail I'm not using. So 16% minus 2.5%, which would give us 13.5%. So 13.5% of the data fall between 8.39 and 9.94. Are there any questions on that one? Okay. And then this is the whole reason I put that one there, is because of question E. Because I wanted to build to a problem. So this one asks us what percent are between 5.29 and 9.94, which builds on the previous two problems. So we're looking at from 5.29 to 9.94. We're looking at that area there. So we're going to use these two results to help us out. So from part C, we know 5.29 to 8.39 is 68% of the data. And we know from part D that from 8.39 to 9.94 is 13.5% of the data. So then, So then to find the percent between 5.29 and 9.94, we're going to take 68 plus that 13.5. Which would give us 81.5%. Questions on that one before I move on? Okay. So just like yesterday with the z-scores, sometimes they'll give you the information you need and you find the percent, or like yesterday you found the z-score. Other times they give you the z-score or the percent and they want you to find the score. So the last two problems are like that. I'm gonna label it really quick. 6.84, 8.39, 9.94. So this time they give us the percent under the curve and they want us to find the corresponding score on the ITBS. So it tells us the highest 2.5% of the ITBS vocabulary scores are greater than what score? So we're looking for the highest 2.5%. So remember from that very first problem we did, if we go 2 standard deviations below and above the mean, that will capture 95%, leaving 2.5% in each tail. And, 95, not 2.5. Gosh dang it, I put a decimal in there and I don't need a decimal, sorry. 95%. And that leaves 2.5 here and 2.5 there. And the question is asking us about the highest 2.5%, which would be this area to the right, or at the top of our curve. And that 2.5% is above 9.94. So highest 2.5% have a score greater than 9.94. Questions on that one? So this last one, it's the same type of question. They give you a percent, but they word it in a different way. And then of course I made a typo, so I apologize. So still working with the same distribution, so I'm gonna label really quick. All right, so here's my typo. We're not ready to do the 32nd percentile. We want to do the 16th percentile. On Thursday, we'll do questions like the 39th percentile. Remember, percentiles mean that that amount of data is below that score or below that observation. So this means 16% of the data are below the score we're looking for. And if we look back, we can see that when we are 1 standard deviation below and 1 standard deviation above the mean, that leaves 16% in each tail. Sorry, I was trying to put my paper down without looking and I knocked other papers over. So we want to know 16% below this score. So that means we're looking at this area over here, and 16% of the data is below a score of 5.29. So a score 5.29 is at the 16th percentile. Questions? No? Okay. Oops, that's not what I wanted to do.